So we're going to tune to higher or lower? Lower, because they're at the bottom. Low clocks are slow. Oh, this was megahertz. This is hertz. Yeah.
Oh, just kidding.
Yeah. Yeah, that's right. Now tell me what the new frequency is. If you're at the top and the radio station's at the bottom, what frequency? Yeah, that's the delta F. Now tell me what the new frequency is. Colleen, do you want a calculator and a whiteboard marker? You're all right, all right. Yeah, that's right. I got 85.1, but
Yes.
I get 8.3 as the shift. Megahertz. Yeah.
Oh, there we go. Calculator error.
Yeah, there you go. You want me to show you how to subtract a couple numbers?
Oh, I had a calculator fail.
Tu calculadora está poseída por el diablo. Yeah, that's right.
Like, you have the right numbers.
Because it's a low clock. You're at the top of the tower. The radio station's down there, so low clocks run slow. That's right. So you make it less. Now, if you were at the bottom and the radio station was at the top, you'd be tuning up the dial, right? That's right.
I'm feeling some plain white
Yeah.
cheese on the banjo. I want to hear it.
I think that's like illegal. That's right. I'll do Mumford and Son when I learn it. That's right, on the banjo.
Yeah, you should definitely.
Plain white cheese on the banjo.
In real time.
Are we good? Does everybody get a delta F of 8.3 megahertz? And then it's a low clock, so it runs slow, correct? Right, so we tune down the dial for that. Let's try this one. Okay. Okay, two trombonists. This is ridiculously difficult, unless you realize that we're at the bottom. Okay? So we're at the bottom of the tower. There are two trombonists. We're at the bottom of this. Shut up! We're at the bottom of the tower, and there's a trombonist at the top, and both of them tune themselves to C. Right? They think they're playing a C. Now, of course, we hear the top player as sharp or flat. Sharp is faster, flat is slower. We hear them as sharp. It's a high clock, and high clocks run fast. So we hear them as sharp, okay? And so let's answer this question. For us at the bottom to hear it in tune, now this person won't hear it in tune at the top, but for us at the bottom, we hear them sharp, and we hear ourselves as a C, right? We hear the normal thing. Should they slide out, that would lower the pitch, or should they slide in, that would raise the pitch? They can just slide out. They need to, right? Now, what are they hearing at the top? They hear the bottom as flat. And then you hear us inexplicably talking like this to them, saying, "You're not in tune. You need to slide out." So they slide out, and they hear it as they hear the low clock is running slow, and when they slide out, they hear their pitches lower. Yes, don't they? Yeah, there we go. Right. Okay. So now, once we've done that, how do we solve this thing? Well, this is the 5.2. Hello? The 5.2 then is, if you recall beat frequency, that's the difference in the frequency. That's what we put in for the delta. Yes? That's delta F. This is the original frequency, and then that's the height of the tower, 250 meters. So now, calculate what G has to be. And it's got to be quite a lot. But calculate that.
Quite a lot.
Newtons per kilogram, or meters per second squared. And we now know their equivalent, don't we? Yeah, that's right. That's what I got. Is that right?
Yes.
8.5 instead of the 12.
Yeah. Dominated.
So now you're solving for G, right? And then multiplying by 2. And when you do that, if you ever need to divide by 10 or 100 or multiply by 2 to get the right answer, say it as though, although it's obvious. Multiplying by 2 gives. So 5.2 over 256, right, equals G times 215, right, divided by 3E8. There you go. Yep. Yep. You got it. Yep. Is a pig.
Yeah, I know. It's not a pig.
Yeah, 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 yeah.
I'm pretty sure it's a koala.
Could be a fat koala.
But
8.5 times 10 to the 12th. Did you square C?
that's Joey.
There you go.
I say we get. We didn't hang this sock up. This is legendary.
I remember when I used to be white.
Look at these.
Oh my god.
Yeah.
Enough to
5.2 is the delta F. Because it's the beat frequency, that's the difference between the two. Yeah. I like that one. That's somewhat convincing. Poor colleagues back there like, okay. You're trying to figure out how to politely leave, you know, the general relativity. Okay, so this is the final formula. I think we can, if we can focus here, I can show you how to do this, or you can maybe figure it out on your own, but I doubt that, right? Okay, so here is, let's suppose this guy has a clock, a little light that's flashing, right? Okay, it's always this way, right? And the time between flashes is delta T naught, and we are over here, right? This person is some distance r from the center of the singularity, and then they are outside the Schwarzschild radius because, of course, we couldn't observe them, right? So if we were to place a graduate student some distance r, right, from the center of this thing, right, and we're observing from some distance, you know, maybe really far away relative to this, right, close to infinity. This really is strictly true at infinity, right? We observe them flashing at delta t, and the formula is that the dilated time, this is gravitational time dilation, is the actual time observed in that frame of reference, 1 minus, right? Okay. Now notice that if, of course, you are within the event horizon, this is imaginary, correct? The second thing you might notice is if you're at the event horizon, how long do we see between flashes? Well, 1 minus 1 is 0, square root of 0 is still 0, and 1 over 0 is infinity, right? In other words, it takes an infinite amount of time at the event horizon to see, yeah, there we go, right? Get it. Okay. So let's do this, okay? A graduate student is 15 kilometers from the center of a black hole with a Schwarzschild radius of 9.5 kilometers. If they are waving in their frame of reference every 3.2 seconds, how often do we see them waving if we are far away, right? I like that, far away. How far? Well, just very far, okay? So we can just plug the numbers in here. It's 3.2 is on the top, right? Draw a little box around this, right? Square root of 1 minus, and since it's the ratio, it doesn't really matter, right? It's going to be 9.5 divided by 15, right? And then that's going to equal our little delta t, right? I've got some cute whiteboards that I don't think we're going to get to, but that's all right. So it's 3.2 divided by the square root of parenthesis 1 minus 9.5 divided by 15. I'll be very careful. What they will do, and I think they gave this to you on the IB test, what they do to trick you because this isn't very tricky, is that they'll sometimes